About 34, okay.
34.
That is the one I saw missing quite a bit. So talk to me about number 34. Tell me what's happening in number 34 first. I don't want givens. That's not a thing that's happening. Say again? You just summarize it. Like what's going on in the problem?
Well, he's golfing on the moon.
Okay, he's golfing on the moon. So we're going to have something relatively flat. We can assume that he's going to hit it up at some kind of angle. Okay. Is anything else particularly interesting happening in the problem, like later in this action?
He hit the golf ball at 1/6.
So okay, that's kind of a known in the problem that we can deal with in a minute. But from a like what's happening standpoint, it's just the golf ball's being hit. That's the whole thing. Is that accurate?
Yes.
Okay, good deal. So now we make the dang T-chart, which I was a little disappointed at the level of not doing that I saw. More people should be making those things for every single question, always, always, always. What do I know? What are some things that are happening here? Which acceleration is 0? Say again?
X.
Okay, why is the x acceleration 0? Because the x velocity is constant, right? But why? What would we need for that not to be true? What would we need for there to be an x acceleration? That is the acceleration. What causes the acceleration? That is the acceleration. What causes the acceleration? A force. So remember, the change in motion thing, that is acceleration. That doesn't cause acceleration. I want to make sure we're comfortable with that. The cause is the force. Something causes acceleration, which happens to be a change in motion. So there are pretty much never x forces in this unit. You are told when they exist. They don't exist here, so our x acceleration is 0. You have mentioned acceleration, so now I'm going to force you to talk about a. Why? Is it negative 9.8 meters per second squared?
No, 1/6.
Okay, it's not negative 9.8 meters per second squared. Why is it not that?
Because
the moon.
It's not on Earth, it's on the moon. That 9.8 is a very special number that only is true at the surface of the Earth, at about sea level. Once you start going away farther and farther from the Earth, the number is actually different. At the top of Mount Everest, it's not 9.8. It's like 9.78. It is actually lighter. Things actually are a little bit lighter up there because it's farther away from the Earth. Moon has much less mass than the Earth does. It's got a smaller radius. That's going to affect its number. So we take 9.8, we divide it by 6. What do we get? Say again?
1.63.
1.63 meters per second squared. It's not a number you will need to have memorized. That will be given to you if you need it. It is negative, thank you. That's still a thing. I got so excited talking about the gravitational field that I forgot we were talking about acceleration. What else do we know? Delta y is 0. Why is delta y 0?
Because it's not like decreasing in the weather, it's going back to the ground.
It's doing a thing and then undoing that thing. It's going up and then it's coming right back down. And anytime we see that kind of symmetric arc motion, if it's not being hit from up above or hit up to a ledge from the ground, then delta y is 0. Okay? Very nice. What else do we know?
The initial speed is 25 meters per second.
So this initial speed is 25 meters per second. Where am I going to put that, x or y?
You need to do the sine cosine.
I've got to immediately find those components. That's one of those things you just do. If you see that something is hit at an angle of this with the speed of this, you should just instantly, like, stop what you're doing, go over to the side, and go crazy with your triangle. What's the angle?
30.
30? Okay. So, let's see, v naught x, v naught y. We're at that point in the year where I do expect you to be able to just rattle off instantly what's going to happen. This is the opposite or adjacent?
Opposite.
It's the opposite, so we immediately write down that Vy equals 25 sine 30. We know sine of 30 is 1/2, so we do that in our heads, and we get 12.5 meters per second. Okay, now we look at the V naught x. We look at the x component. Is that the opposite of adjacent? So we immediately write down 25 cosine 30. What number is that?
21.7.
21.7 meters per second. Okay, do we know anything else? Remember that when I asked that during the homework time, it's a genuine question. I haven't read this problem in days, so I really don't know.
We don't have time for the changing that.
Okay, so we don't know a bunch of stuff. Do we actually know anything else? He is not here.
We can find time on the website.
Okay, so now we're thinking strategy, but just to double check, we're done solving this, right? Okay, so we recognize how these problems normally work. So we're pretty confident that we're going to have to find time with the eventual goal of finding, what are we finding?
Delta.
And how do they phrase that in the problem?
How far did it go?
How far does the golf ball travel? Okay, nice. So we're going to need to find time first. Based on our list over there on the right side of our time variables, what equation do we have that matches that list?
Change of y equals u of t plus one t squared. Make sure
Our absolute favorite one. Everything is y. Can we cross the normal stuff out here?
we can no.
Not really. Because at this point in this unit, there's no normal stuff to cross out. Sometimes stuff is 0, sometimes it's not 0. We just got to deal with that as it comes. Is anything 0? Okay, so when we plug that in, it goes away. Let's see, 12.5 t plus 1/2 times negative 1.63 times squared. By the way, another reason I'm so nitpicky and annoying about find these velocity components the instant you realize there are components, it is so easy. Even for me, it is so easy to get like really excited and go and plug in 25 right here. It's very easy to make that mistake, and it screws up your entire problem. You're going to miss almost every point just on that mistake. So we're going to solve this by rearranging, what does that turn into? Negative 0.815 t squared. What can we do here?
You can cross out the well, 1 t on
Okay, so I'm going to divide both sides by t. What happens over here when I divide by t? Okay, that one just straight up goes away. It turns into a 1. What is t squared divided by t?
t squared.
Just t. Okay? So I'll go ahead and cross out the negatives as well. And I end up with t is 12.5 divided by 0.815. What do I get? Say again?
15.337.
15.37 seconds. 3-4. 15.34 seconds. Okay, good. We're doing good. Now what do we do? Plug it back into... Okay, so now we're going to use this same number over here on our x side. And just as a good problem-solving strategy, we are always writing down time once we get it. We kind of know the game by now. We are going to use this guy because that's what we have on the x side. When we plug our numbers in, we're looking for delta x. V naught x is 21.7 times a time of 15.34. What's going to happen to this term over here? Why? Because the x acceleration is 0. Why? No, that's not why. Why is the x acceleration 0? There's no x force. There's no x force. So we multiply blah, blah, blah. What do we get? 332. It annoys me that that's not rounded to 333. I like that number better. So we're going to say 333 meters. Get a nice triple ball. 333 meters. Okay, we've done it. Hooray. Again, that problem, way harder than anything you saw in the first unit. Focus on how much you are improving and growing. It's a good thing. Is this all this problem asks? Okay, but is this like part A or something?
You just solve part B.
Okay, so we solved part B. Great. Now what?
It says ignoring the arrow means how much farther would it travel?
Find how far it went on Earth.
Okay, so we're comparing it to how far it goes on Earth. So we're going to do the Earth version.
Wouldn't it just be 6 times?
Just change the y acceleration.
Good question. Wouldn't it just be 6 times on the moon? Not exactly. You want to be very careful with that line of logic, especially with these formulas. These formulas have times squared in them. And so you want to be very, very, very careful whenever you're just trying to multiply or divide by 6. Generally, if you have numbers, it is a good idea to go back in and actually plug stuff in. But I've already heard a few people say it. What is the only difference between everything I'm going to write down here and everything I've already written?
It's just the gravity acceleration of y.
The y acceleration is negative 9.8 instead of negative 1.63 meters per second squared. Nothing else changes. Nothing else is different. The process is exactly the same.
I was just gonna say the time changes.
Well, the time will change because of that, right? But the process is the same. Your numbers will obviously be different. But this is the only thing that you have to kind of know to make different. And then, honestly, you just do the problem again. You do the problem again. You're going to get, what do you get for, like, what do you get for the delta x on Earth?
275.380.
276 meters. Is that your final answer?
Wait. That's how much. That's the difference.
Ah, okay. So what is the delta x for the Earth then?
I think.
Okay, so it goes 55 meters.
Yeah.
Are we done solving it yet?
No.
The question asks how much, like, what's the difference, correct?
Yeah.
So you need to actually find the difference.
Yeah.
So your answer is going to be the 333 minus 55. That'll get you some number. I don't care what the number is. Do we have any other questions about the book problems?
Can we do
Number 28. Talk to me about 28.
my question is here, just do it. I'm gonna do it.
Oh, number 28 is kind of a common way of asking a question. A ball rolls off of a table. What is different about this problem? You guys remember the first example problem we did in class with the marble being launched from the marble launcher at a height of 1.5 meters?
Yeah.
What is different between that problem and this problem? Delta y is different. A number is different. Is anything else different? No. That's actually, like I said, a relatively common way to phrase a problem. A ball is rolling, but it says it's like rolling forward at a speed of what? 1.25 meters per second. Off of a table that has a height of what?
1 meter.
And then it says two things, I think. What is the time it takes for it to reach the ground? And how far does it go before it hits the ground, correct? So again, we're kind of doing the same thing we do for all these problems. We are finding time and then using time to find delta x. So if we go through here and set up our t-chart, we have the x side, we have the y side. No matter how easy or simple the problem looks, we're always doing that because we're not good enough to get away with not doing it. What do we know on each side? Okay, so the initial velocity of x is 1.25 meters per second. And we know that because it was doing that before it left the table, so the instant it leaves the table, what is it still doing? That. There's nothing to change that yet. Nothing really to change it ever. It's not slowing down, and so it's just going to keep going. I heard someone talk about delta y. What is delta y? Oh, let's get that unanimous. What is delta y? Negative 1 meter, because it's falling down. What else do we know?
The initial velocity for y is 0 meters per second.
Because why?
But there's only an x force on.
Not an x force. There isn't an x force. It's not moving in the x direction yet. Sorry, it's only moving in the x direction. It's not moving in the y direction yet. It's only moving horizontally. It rolls off of a horizontal, a flat table. If it rolled off of some weird slanted table, would that be true? No, then we would have like some components and do some weird stuff. It might be a good problem actually. But,
Don't you dare.
oh, it's not, it would be hard. You do the same way you do anything else. Find the components and then do math. But since it's rolling off of that flat horizontal table, it's not moving up or down yet. Since it's not moving up or down, the up and down velocity, the y velocity, is 0. What else?
Acceleration of y is negative 9.8 meters per second squared.
How do we know that?
Gravity.
The force of gravity is acting on Earth. accelerating things down at a rate of that. Is anything pushing on it in the x direction? No. So the x acceleration is 0. So we have that stuff, and now we just go forth and solve. Oh, I want to talk about the ranking task. This was a very, very easy ranking task. But I am willing to bet that 95% of you got it wrong.
I think
It was on campus. Okay, so let's think about the way we've solved these problems in the past. What matters? What affects how long it takes for for any object to get to the ground? The height, so the delta y. What else? Which speed? Nope. Nope. If I tell you that we know these things, let's do the first one. The initial x velocity is 5 meters per second. The delta y is negative 40 meters. Ay is negative 9.8 meters per second squared. Ax is 0 meters per second squared. V naught y is, what is V naught y for all of these? Why is it 0? It's moving which way?
In the x direction.
It's moving only in the x direction, which means it's not moving in the y direction. So if we look at that and I ask you to find time, what are you going to use, the x or the y side? You're going to use the y side, and you're going to get to this equation. So you're going to use this equation, and that is going to be the basis for you finding time. What is this term going to be?
0.
Is that going to change for any of these, A through F? Why?
Because they all have the same coordinate.
They're all moving only in the x direction. They're all moving only x, which means there is no y direction, which means we can rearrange this and solve for time and get 2 delta y over ay, square root all of that equals time. What does the time depend on? Looking at that.
Delta y and acceleration.
The height and the acceleration. How does the acceleration of all of these compare? They are all the same. The acceleration for all of them is what?
9.8.
Negative 9.8 g. Okay. What about the delta y? How do A, B, and C compare?
Twice as big.
So no, they're twice as big as each other. How? Just these three up here. How do A, B, and C compare? They're equal, so their times should be equal. Now, will any of them go farther?
Yes.
Yes. This one will go the farthest horizontally. This one will go the mediumest horizontally, and this one will go the shortest horizontally. But when will they hit the ground relative to each other? At the same time. What about these down here? Don't compare them to the top, just what about these down here? Same conversation. It's the same height, and height and acceleration are the only thing that matter in this formula. And so that's all we care about there. So these all hit the ground at the same time, and they happen to go different distances, but what are we trying to rank? The time. So we have this set being equal, and then we have the bottom set being equal. Which set is going to have a longer time? We're supposed to rank longest first. Okay, why? Prove it mathematically.
They have the big delta y.
They have a big delta y, and delta y is in the numerator of the formula. It is a square root relationship. As delta y gets bigger, time gets bigger. So all of these are greater than that. We're going to pretend that that was good notation. And that's it. That's the whole thing. How many of you got that right? Oh, you would have gotten it right. Okay. Oh, come on. So we talked about some stuff. Centripetal means towards the center of a circle. Centripetal acceleration. What's our deal there? Which way does centripetal acceleration point?
Outward towards the circle.
Towards the center of a circle. It points towards the center of a circle. Anything with the label centripetal always points towards the center of a circle. So the centripetal acceleration points towards the center of the circle. And what does it do? What is the effect of any acceleration? It changes the motion. It either changes the speed or changes the direction. It changes one of those things. So the centripetal acceleration, A sub c, C for centripetal, means like that is the actual physics thing that changes the definition of the velocity. That is the effect of circular motion. It's what makes the motion go in a circle. Causes a change in a straight velocity, and it pulls that straight velocity into a circle.
What's an example of
So I'm swinging this around like this. What causes accelerations, by the way? What causes acceleration? Force. Remember, change in motion is the acceleration. Change in motion cannot cause acceleration. Change in motion is acceleration. So, am I applying a force here?
Yes.
How am I applying a force? Which way am I pulling? Towards the center. Hey, by the way, that's going to be a thing in a minute with that word centripetal. So I'm always pulling towards the center. How am I changing the velocity? Always which way? It's a hard question to answer. How am I changing the velocity? I can't change it counterclockwise. I can't pull counterclockwise. I can only pull in one direction at once. Can I get somebody else up here real quick? Okay, so what I'm going to do is the same thing I did with Ben, but on a slower, it sounds like, oh crap, on a much slower speed, so you can see what's happening. Now, I want you to walk straight towards the back of the room. Okay, if I pull her, is she going to keep going in that direction? No, okay, so I want you to walk that way now while I pull this way, and let me wait. So go. Okay, I pulled towards me. What did she do? Straight towards me? She curved. She curved. So let's do that again. Walk that way. I pull towards me. I keep pulling 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 towards me. Every time I pull towards me, what does she do? She curves. She's moving, and I pull. She turns this way. She's moving this way. I pull towards me. What do I do to her velocity? Change it this way. I pull towards me. I change her velocity again this way. I pull towards me. I change her velocity again this way. Each little pull towards the center is always pulling the velocity vector. It's kind of curving that arrow around it in a circle. Thank you. I will expand on that just a little bit when we define the next one. I want to get through centripetal acceleration first. Our definition for centripetal acceleration is not the same as our definition for just normal plain Jane acceleration. It's not the same thing. What did we say mattered out there for making it hard to go in a circle? The mass matters, but believe it or not, the mass is actually what makes it harder for me. It doesn't really affect what they're doing, believe it or not. So the radius matters. What else? Well, the force is what I'm doing. The velocity. The farther out you are, it gets kind of tough. And then the faster you're going, it gets kind of tough. So this combines through some calculus magic that we're not going to get into to centripetal acceleration equals velocity squared divided by r, the radius. Velocity squared divided by the radius. So you know what AC is. What would the units for this be? It's acceleration. It's still meters per second squared. What is r? The radius of this circular motion. What are we going to measure that in? Meters. And then this V. Bless you. This V. The velocity, right. Now, velocity is speed and direction. If we have a centripetal acceleration, the object's moving in a circle, right?
Yeah.
Is the velocity constant? If something is moving in a circle, is it constantly at the same speed and direction? No. What's changing? The direction. The direction is changing. The motion is changing. That's why there's an acceleration in the first place. So the vector of velocity does change, but the value does not. The speed, the magnitude, does not change. So this, we're going to call it the tangential velocity. It is much easier than you might think. Bear with me. It is, however, still velocity. It is still measured in meters per second squared. All that word means is that it's for something moving in a circle. It deals with the tangent line.
Because the velocity goes
It deals with the tangent line. That's all we're going to deal with for now. Now, this tangent is not the SOHCAHTOA tangent. We don't have to do any trig here. We don't have to do any angles. So we've got centripetal acceleration. We need to add in like another vocab word before we really pull this together. So I'm going to go ahead and do that. The centripetal force. This is the thing that I'm doing. Okay, now, the deal with centripetal force. There are certain topics in physics that are normally explained one way. Newton's second law is one of them. It's always explained the exact same way. Centripetal force can be explained a few different ways. Ayers and I are pretty similar on it. But textbooks, the internet, not so much. There's different ways to explain it, some of them good, some of them not so good. And so if you find some explanation, you're trying to figure out your homework, so you're in your textbook, you're on the internet trying to find centripetal force explanation, you might find something that looks different than what I'm about to tell you. Come talk to me and we'll hash out the difficulties. They're probably still right, it's just ways you're not used to phrasing it. What we're going to say centripetal force is, it is the net force. That is the most important part of this definition, by the way. It is the net force that causes circular motion. So, how are we going to make the variable for this? Since it's centripetal, what do we know is going to be there?
Acceleration.
Well, yes, but that little c subscript for the variable specifically. So there's definitely going to be, don't write this yet, an FC. What else is there going to be, though? What else is important in that definition that we need to put in our variable? Net, so sigma. And again, I will continue to mock and make fun of you if you call that an E. It is a sigma. Sigma FC, net force. The C just tells you it happens to be a centripetal force. Is any net force a centripetal force? Can you have net forces that don't cause centripetal motion? Yes. Is any centripetal force a net force? Yes. It must be. Any centripetal force is a net force. And so if I ask you to calculate the centripetal force, you can do it by adding up some forces. You can do it by expanding this into this force minus this force plus or minus this force. There is no such thing as a centripetal force. Sometimes you will find terrible explanations that use that as some logic. It's not. Forces are forces. The force of gravity is a force. The force of tension is a force. The normal force is a force. Those forces, if we put them together in the right lovely little package, can cause centripetal motion. But that doesn't mean you would ever put centripetal force on a free body diagram. Would you ever put the net force on a free body diagram? No. You put individual forces, you put a whole bunch of small arrows, and then you build the net force off of that. We're going to do the same thing right here. What are the units going to be? Still newtons. What is any net force equal to? If I want to give you an equation for this, which I do, what is any net force equal to? Mass times acceleration. Well, if this is a centripetal force, what kind of acceleration is it going to be? It's going to be a centripetal acceleration. A net centripetal force will cause a centripetal acceleration. This is not on your formula sheet. Now, Newton's second law, this is on your formula sheet. That is on your formula sheet. What do you need to do to make that a circular Newton's second law? You need to have centripetal acceleration. You need to have a centripetal net force. And you probably want to do a little bit of rearranging so that it looks like that. By the way, do we see how we're going to do some two-step problems here? We're going to find centripetal acceleration, then we're going to plug it in over there. Remember how we talked about how it was harder for me for a bigger mass? That's this. I had to apply a bigger net force if the mass was bigger. I also had to apply a bigger net force if the velocity was bigger, because the big velocity meant a big acceleration. That big acceleration required a bigger force no matter what the mass was. Yes, ma'am? That one is on the formula chart, yes. And it is labeled AC, I'm almost positive. Let me actually double check that. If not, that is, yeah, it is. It's AC. It looks exactly like this. So now that we have all of our values, now I'm comfortable answering Taylor's question from earlier a little bit better. I want to draw a circular motion. And I want to talk about an object in 4 different spots. Don't worry about if this is horizontal motion or vertical motion or diagonal motion or whatever motion. The issue is that it's moving in a circle. And since it's moving in a circle, we can say a few different things. Since it's moving in a circle, we can automatically say a few different things. What has to exist to cause this object to move in a circle?
Acceleration.
An acceleration. But remember, that acceleration is the change in motion. What causes the acceleration?
Forces.
Force. And if this is moving in a circle, is there a net force?
Yes.
Yes. You must have a net force to cause an acceleration. What kind of special net force is it? It's a centripetal net force. So, before I start throwing a bunch of arrows up there, I first have to ask you a question. Right now, I am swinging this horizontally towards you. A lot of you guys are like, oh dear, I don't like this. I've seen how clumsy Mr. Brown can be. So, I'm swinging. Talking about the motion. Okay, it's constantly changing. How is it changing?
Direction.
It's changing its direction, not changing its speed. Its speed is constant. Am I always pulling in the same direction? No, look at what my wrist is doing. It's hard to keep my wrist in the exact same spot, so technically this kind of messes things up a little bit, but my wrist is always having to pull back towards the center. By the way, I'm pulling on the rope, so what is the rope doing? Pulling on me. That's why my wrist moves, because the rope is pulling back on me. And so as I'm pulling on this thing, I'm constantly changing the direction back towards the center. And so the last question we have to answer, or let's say second to last question. Right here, which way am I pulling? This way. I have to pull towards the center to change its velocity. Right here, which way am I pulling? towards the center. Right here, which way am I pulling? Towards the center. Right here, which way am I pulling? Towards the center. Since the net force right here is towards the center, we can call it a centripetal force. Since it's a centripetal force, what is it going to cause? A centripetal acceleration. That's what causes the circle. Since it's a centripetal acceleration, which way does it point? Towards the center. Right here. Just right here. It points towards the center. Where does it point right here? What about right here? What about right here? What about right here? No matter what circle I make, no matter what's going on, the centripetal force and the centripetal acceleration always point directly towards the center. Where it gets a little bit weird, let's think about this motion again. And I'm going to stop it right there. Which way is it moving right there? It's moving towards the center? So it's going like this? It's moving this way?
Moving around.
Let's ask it this way. Let's say that Shannon is just annoying me today. I don't know why. She's an annoying human being today. And I want to hit her with my makeshift sling. Where do I let it go so that I can hit her?
At the side. Like, no. No.
What's going to happen if I am dumb and don't know fists and I think, okay, I'm going to hit Shannon. I'm going to let it go when it's facing her. So I want it to hit her. So I'm going to aim it right at her. What's it going to do when I let it go right there? Goes that way. Well, why does it go that way? It was pointing at Shannon. Because it's still moving. Because it's always moving. What do forces do? They cause a change in motion. And if I let go, I'm no longer changing. So if I'm no longer applying a force. So if I'm no longer applying a net force, is there anything to change the motion of this masking tape? Ignore gravity. No. And so what is it going to do when I let it go? It's going to do the exact same thing it was before. So if I let it go right here, right as it's facing Shannon, it moves straight off that way, tangentially to the circle. It makes a tangent line. That's why it's called tangential velocity. Yes. So as this is moving around, this is a top-down view of me. Shannon is right here. Where is it moving right at that point? To the right.
Yeah.
It's moving to the right. So the tangential velocity right here points that way. Okay, well, what am I doing to the masking tape at that point?
You are.
Well, let me rephrase that. Before I try to hit Shannon, what am I doing at that point? I'm swinging it and I'm pulling it. I'm having to apply a force. Which way is my force?
Towards the center.
Always towards the center.
Is this a free body diagram?
Kind of. It's like a bunch of free body diagrams on one picture. Okay. What is that centripetal force causing? A centripetal acceleration, a centripetal change in motion. And that also is going to point towards the center. Those arrows don't need to be the same size. They're not the same unit, which means they're not going to be this. I mean, you can't compare them at all. You can't compare apples and oranges. Okay, so we have a velocity. We have a velocity pulling this way. What happens when we have an acceleration acting on a velocity? Now, you guys keep wanting to give me this answer. Now you actually get to give it. What is an acceleration? It is a change in motion. What causes an acceleration? A net force. So that acceleration changes the velocity. If I throw this horizontally, it's going to curve down because of gravity's influence. If this is pulling towards the center, what is it going to do to this velocity? Is it going to make it start going straight towards the center right here? It's going to curve it. Now, we could draw this at a whole bunch of different stages. But at the next stage, right here, where will it be moving? Down. Tangent to the circle. Now, I know that a lot of you had a relatively tumultuous relationship with geometry. Do you remember what the word tangent means? It's a line that only touches the circle at one point.
Oh.
So that is a tangent line. And that line obviously extends in both directions. We just pick the direction that it's moving in.
So like when a cannon launches the ball and it curves down
Mhm.
because there's two forces, is that why it's curving?
It's the difference is that
It's
the force of gravity is always pointing the same way. Here, which way am I pulling as it comes around here? Has my force changed? I'm pulling towards center again. So which way are my forces right here? I'm creating a centripetal force like that. And then I have a centripetal acceleration like that. Also, bad Mr. Brown, I got lazy. I forgot to include the net right there. So you need to go back in and
I
fix
thought
that
you
real
don't
quick.
include that.
It's not really a free body diagram. That's the thing. You also wouldn't include velocity or acceleration on a free body diagram. This is just a vector diagram. It shows which way stuff points at different spots. Which way? I'm going to switch things up on us. Sorry if you've already drawn those dots. I'm sure you have. You don't have to erase them. Just don't draw anything on them. Which way is the centripetal velocity, or the tangential velocity, right here? So it's definitely going to be on this diagonal line. Is it going to be up and to the right or down and to the left? Down and to the left.
Centripetal.
Yes, ma'am. I'm going to take you back outside and swing you around if you can't wake up. What else is acting? Or what else is going on at that spot? Is something pulling on it? Yes, because if not, it's not going to keep going in a circle. So we must have a net centripetal force in towards the center. What else must exist? A centripetal acceleration, which is the effect of the force. I would like you to now draw all three vectors on that last little bit.
So at any point in the circle, the arrows are going to be the same?
Yes. Yes, all three arrows are always the same. Their numbers don't change, only their directions change.
You're drawing it this way because that's the way you're swinging it.
Yes. You don't have to draw that. I'm not going to do much on it. Okay. Let's do centripetal acceleration. Which way does that one point? Towards the center. Always towards the center because the change in velocity is always towards the center. What causes the centripetal acceleration? Get it right? A force, a net force, right? So that net centripetal force causes the centripetal acceleration towards the center. And then that's going to change the velocity. But what is the velocity at that instant in time? Give me a combination of up, down, left, right.
It's like it's
Up,
up and to the left.
and to the left. Okay, why is it not down and to the right?
Because you're swinging it.
Because it's moving like this. What would be the velocity vectors if I changed the direction of rotation? Okay, so it would be the direct opposite. So up here it's moving straight that way, straight that way, straight that way, straight that way. What would change about the centripetal acceleration and the centripetal velocity? The centripetal acceleration and centripetal force? Nothing at all. Those always point towards the center. How are we feeling?
What happens when you release it? How does the vector?
It moves. So Tanner just asked what happens when you release it. It moves in the direction of its velocity at that point.
What about?
Notice that when I let go, every time I let go out there, they would fly off in a straight direction. They would fly off in a straight line.
So how would the vectors like the?
Well, if you let go, there is no longer a net centripetal force.
Okay.
And so the force vector and the acceleration vector completely go away. Now, when I introduced what we were talking about, I mentioned that this is just like a second part of Newton's second law. This is really still just Newton's second law. The only difference is that before, when I asked you to calculate acceleration, a lot of times it was delta v over t. Now it's v squared over r. The logic is still very, very similar. So what I'm going to do is give you an example problem. I have a pendulum. That pendulum is swinging. It is being swung at a constant speed. But we don't, we do. The length of the string, 1.5 meters. And I'm going to say that it is swung at a speed of 3 meters per second.
So what do you want?
Nothing yet. I am then also going to give you the mass of the little bob, 0.5 kilograms. Your first step is to find the centripetal acceleration. Your next step is to find the net centripetal force. Go.
What? No. Stop.
I gave you equations. Use them.
How do you find a balance?
Is there a certain direction positive?
Don't worry about that.
So it doesn't matter whether I just do
Oh, no, it does. Because Newton's is still kilogram. Newton still uses kilograms.
So if it's in grams, switch to kilograms.
Yes.
And then we need net force.
You're finding net force. That's part B.
So what happens if it's changing in motion and it's changing in speed?
You won't ever have to solve problems like that. Like what you might be seeing is like this. This is what you're asking about, like it's changing motion and speeding up, slowing down. You're always going to be told it's moving at a constant speed. It's actually very difficult to do it the other way.
I know.
When you give this length, will it be in a capital L like you could?
Capital L or lower L.
Okay.
Just depends. Sometimes I'll give it to you lowercase l. Always. So, what do we need to calculate centripetal acceleration? What kind of things directly affect centripetal acceleration? Okay, velocity and radius. So at this stage, early in the unit, we're pretty comfortable only just using that basic equation. What is the velocity here? Okay, that's 3. That's easy. We're going to square that. We're not going to forget to square that for some dumb reason, even though you do all the time. R, the radius of this circle. So for this, I will bring up my handy-dandy masking tape. As I am swinging around my handy-dandy masking tape, what is the radius of this circle? Is it the length of the string, or is it half the length of the string? Or is it double the length of the string? It's the length of the string. It's swinging around my finger. My finger is the center point. It's either above or below, above or below, above or below. That's why you don't have to divide by 2. It's not doing, watch the thing, it's not doing this. If it were doing this, then the length would be the diameter, but it's not doing that. It's going around my finger. My finger is the center. This point is the center, which means the radius is 1.5 meters. So 3 squared gives us 9, divide that by 1.5, and we get 6 meters per second squared. There we go. Not too bad, right? Okay, so now I want us to calculate the centripetal force, the net centripetal force causing this motion. Now, I want you guys to think about
Oh.
forces here. As the bob is swinging around, what forces are acting on it? So the force of gravity. What else?
The central force.
Is that a special individual force? No. So we can't say, and I want everyone to hear this real quick. You can't say the centripetal force is acting on it. The centripetal force is an effect. That's just the net force. There's a force of gravity acting on this. What other force is acting on that? It's connected to a rope.
The force
There's a
of tension.
force of tension. So we have the force of gravity. We have the force of tension. Are either of those the centripetal force? No. No. They combine to make the centripetal force, but neither of them are individually the centripetal force. So we need to go, we're not even going to go that deep. This is just calculating the whole net force. When you're asked to calculate centripetal force, they might as well just say, calculate the net force. And what is net force always equal to? Mass times acceleration. In this specific case, what is the acceleration? It is centripetal acceleration. And in this specific case, what is that actual centripetal acceleration?
6 meters a second per second.
We just figured it out. It is 6 meters per second squared.
Wouldn't you convert the kilograms to grams?
No, you would never convert kilograms to grams. You might be thinking about converting grams to kilograms. So we get a net centripetal force of 3 newtons. That is the net force acting on that thing. Is the force of gravity 3 newtons? Is the force of tension 3 newtons? What about tension minus the force of gravity? That's going to be 3 newtons.
So why don't you explain?
We don't need to. What this is asking is just do that. Now, what I could ask you, what is the tension at the bottom of the motion? What is the tension at the bottom of the motion? Now, if I asked you to find the normal force of some cart rolling around on the ground, what would you instantly do?
Free body diagram.
Free body diagram, and then what? No. Not a system. Y'all are overthinking this. Newton's second law. Free body diagram, Newton's second law. I'm asking you to find tension at the bottom of the motion. So right there. Let's do a free body diagram on that thing. What's acting on that little ball? We've already said it. There's the force of gravity pulling which way? Okay, what else is there? Force of tension. How does the force of tension always point?
Opposite of gravity.
With the rope.
With the rope.
The tension always points with the rope. Which way is the tension right here?
With the rope.
Up and to the right with the rope. Which way is the tension down here?
Directly up.
Directly up with the rope, right. Are there any other forces acting on this? Is there a normal force? Y'all make that mistake on your test a lot. Is there a normal force right there? No. Stop calling any force that points up a normal force.
Centripetal force.
Is that
That's
a
the net
separate
force.
third force? That's the net force. The centripetal force is it is the net force.
Okay.
We never put that on our free body diagram.
So the
That's the side effect. That's what we get when we combine both of these. So now what I want us to do is find the force of tension. So we're going to do Newton's second law. Net force equals mass times acceleration. Now, every time we've ever written down net force equals mass times acceleration, I've asked you a question. Which direction is it? Normally the choice is X or Y. But now, what direction are you going to tell me? It's the centripetal direction.
what?
It's the centripetal direction. It's anything that deals with the center of the circle. That's all we're doing. We're just saying that in this specific case, we don't care about X, we don't care about Y, we care about the circle. We care about what points towards the center and away from the center.
So is that like the combination of X and Y?
Kind of. It's more just the ignoring X and Y. X and Y don't have any meaning. We only care about the stuff that's this way. Up here, we would only care about the stuff that's this way. So, net force equals mass times acceleration. That's always true. What can we do after we write down net force equals mass times acceleration? We can expand. We can expand the net force term. So based on our free body diagram, let's expand that. What does this expand into? How do these compare?
Force of tension minus force of gravity.
Do you put FTC or do you say F?
No. Good question. You do not say FTC or FGC because neither of those is the centripetal force. What is the centripetal force here?
Combination of them.
FT minus FG. This makes the centripetal force. Okay, so now let's keep expanding. Do we know FT?
We can find it.
We're going to find it. Do we know FG?
Yes.
How can we figure that one out?
FG equals mg.
Mg, okay. Equals, we know M. Do we know AC? If we didn't know AC, what would we do? Go off and find it, just velocity squared divided by R, right. But we already have it, so we're good there. So Ft equals MAC plus Mg. What's the mass? 0.5 times 6 plus 0.5 times 9.8. Say again? 7.9 newtons.
So, if you had to find the force of tension up there,
You would.
you would.
So why isn't 9.8 negative, but it is when you're talking about aerodynamics?
Because G is a strength. It is how strong gravity is at a particular point. Right here at the surface of the Earth, it has a strength of 9.8. And we don't care about the negative. You say it's negative when you draw this arrow. For kinematics, though, the fact that that acceleration points down, that's when it starts mattering. You could write it as the acceleration due to gravity is negative G. It's negative 9.8.
So, we'll never have to find the force of tension at like an angle or anything. It'll just be like straight up and down.
You may have to find the force of tension at an angle, but it will. I don't believe you will have to do it in this unit. It will be it'll be like some other just normal Newton's second law thing.
And if it was directly above, like it was directly above, so force of gravity and force of tension were both going down, it just gives.
We're about to do that.
Why is there not an applied force in the force?
Say again?
Why is there not an applied force in the force?
The applied force is the force of tension. I'm pulling on the rope, but the rope is what's pulling on the pendulum. Okay, so now we're up at this point. We're up at the top of the circle. What is the velocity?
Are we using the same one?
Yeah, this is the same. This is like part whatever of the problem that we just did.
Velocity is 3.
Okay, so the velocity is still 3 meters per second because that's always constant. What is the length of the string?
1.5 meters.
1.5 meters. No reason for that to magically change. The pendulum is still, of course, 0.5 kilograms. And now what I want us to do is find the tension at the top. Now, I will warn you. This is going to get a little bit weird right here. Let's think about Newton's second law right here. We're obviously going to start with net force equals MAC. But now let's think free body diagram. What's acting on the pendulum?
Tension and gravity.
Okay, I'm going to deal with gravity first. Which way does gravity point?
Downward.
Gravity is going to point down, so FG points down. Which way is tension going to point?
Down.
Down. How does tension always point?
With the rope.
Now it always points with the rope. So tension points down. So we're going to have two downward forces
You add
and no upward forces. So when we expand this, how are we going to expand that? Let's make up positive just like normal.
Negative FT minus
Negative FT minus
70.
FG equals MAC. Well, negative FT minus MG equals 0.5. And then what are we going to use for the acceleration if we make up positive, which way does the centripetal acceleration point over there? It always points towards the center. Right here, which way is towards the center? Down. And down is negative. Which means your centripetal acceleration will be -6. Because the centripetal acceleration points down at the top. We're going to get a lot more practice in with this. This is what makes this unit hard, is that specific thing right here. You're going to get better at it. We're going to get lots of practice in next class. Go ahead and put your things away. That is that.
Why don't you